All right, 4.2, which I actually do 4.2 and 4.7. I know 4.7 is at the end, but I won't be doing another video set for 4.7. Everything that I do here in 4.2 incorporates the same thing that they talk about in 4.7. So when you get to 4.7, I don't have any specific guided notes for those, so you'll have to make sure you watch the online My Math Lab videos. But the stuff they do there is the stuff that I do here in 4.2. And so I do a little more in 4.2 because I kind of combine the two sections. Whereas they only cover sort of the geometric stuff in the left hand, I do both, left, right, and the geometric. So I kind of do everything here in this one section. All right, so area under the curve. All right, this is what we're getting into to lead us to the fundamental theorem of calculus and definite integrals. All right, so first, the reason why the integral symbol is that S shape, right, as the S shape of my function f of x dx. The reason why is because it comes from the fact that it's an accumulation function. What this S shape represents, so what we're going to get into in the next couple of sections in the fundamental theorem of calculus, is that this integral symbol, when I look at it specifically from some point A to some point B, from so input values, what it is, it's the sum, the infinite sum of every single function value from one point to the other. And what it translates to is area. All right, and that's what we're going to get into. So that's why this has got the S symbol, because it's an accumulation function. It's an infinite accumulation function. All right, which is, again, what we're going to talk about here in the next few sections. It actually takes us a few sections to get through. All right, so what we're going to first talk about is making sure you understand areas and graphs. All right, so because that's sort of a big, it's kind of like when we talk about rates of change and slope. That's big to connect the two. All right, slope of a tangent line, slope of a function, rate of change, derivative. Same thing here. Area of a function, area under a curve of a function, relates to definite integration, right? Accumulation of function values. Right, so first we'll talk about the area part, which again, area is something you should be familiar with. So suppose I have an example where I know that the consumption of oil is constant, meaning it's the same rate. They consume oil at the same rate over a 4-year period. Suppose that consumption rate is over the 4 years, T represents years, is 1.2 million barrels of oil consumed per year. All right, so that's a rate of change. It's a derivative. That's how fast this particular region is consuming oil every year, and it's the same, so it's constant. Same speed, same increase in the rate of oil. All right, every year. All right, so it's a derivative. So, and I'm going to graph it in a second. So what that translates to is if I find the area of the region under that constant curve, they consume, since they consume 1.2 million barrels per year for 4 years, so every year they consume 1.2 million barrels. So I take 1.2 times 4, and so it means over the 4-year period they consumed a total of 4.8 million barrels of oil, right? And so where it comes from is every year they consume 1.2 over the 4 years, the change in years before, and so you get 4.8 million barrels. And then we're going to translate that to area. How do you can understand that with area? All right, so remember the rate of change function, f of t, was 1.2 million barrels of oil per year. And so again, if I draw that out, this would be time in years. And again, it's only over 4 years, so my function's going to start at 0, stop at 4. This would be the million of barrels of oil per year. And so again, I'm just going to mark off up here. That would be 1.2 is where we start. And so the function starts here at 1.2, goes over here to 4 years. Again, it's constant, right? F of t is the constant function 1.2. Right? That's the constant function. And if you look at this area is a rectangle, right? This area here is a rectangle, which is the total, and again, the area comes from, let's just do the base times height, right? Area is base times height. Well, the base would be 4, right? 4 across, the height would be 1.2. And so area would be 4 times 1.2. And if I put units on that, it would be 4 years, right? 4 years times 1.2 million barrels per year, right? Per year, which would be per is divide by. Right, that's the unit. And so the years cancel out, and so when I take my 4 times my 1.2, the area does represent the 4.8 million barrels of oil consumed. The total, right? That's what it represents. And so that's trying to get you to relate area under the rate of change function is the sum of the consumption, right? The total sum consumed over those 4 years. So when I take the area under the curve, I'm finding the accumulation of all the function values over those years, and that's represented by area graphically. Alright, well, suppose it's not such a pretty graph like the previous. The previous one was a nice rectangle. We know the area of a rectangle, right? We can find that pretty easy. Base times height. It's one of the easiest areas to find. Well, suppose, though, we're given a cost function that's not so linear, right? That's not nice and pretty. Cost goes up and down. Alright, suppose this cost function is represented by this green function here. Alright, so this would be the derivative. So x would represent my items, and this would be the cost in dollars per item. Alright, well, suppose from 0 to B, right? That's what I'm looking at. So I start at 0 items produced up to B items. And I want to know how many items were produced total, right? If I want to find what that area is, well, it's not a nice geometric shape now, right? It's not a rectangle. It's not a base times height. It's not a triangle. It's not a trapezoid. I can't find it easy using my geometry. Alright, and I can't find the area, which the area would represent the cost, the total cost from 0 to B. That's what it would represent in dollars, right? That's what it would be, because if we found that area, it would be my rate of change, my derivative, which is dollars per item, times the change in x, which would be items. Items cancels out and leaves me with dollars, right? That would be the units on it. And so we want to find, well, what's that total cost then? We want to find the area in the curve. Well, the area, and again, the area gives you total cost in dollars from 0 to B items. How do we find it? How do we find that total cost? Well, that's a problem because I don't have a nice picture. I don't have a triangle, I don't have a rectangle, I don't have a trapezoid, I don't have something where I've got a nice geometric formula like the last example. Alright, and so that's what we're going to get into in this case. It's actually going to be solved by a special type of limit which involves an integral. It's called the definite integral. We'll get to that in fundamental theorem of calculus. We won't get to that until the next section, but this is sort of the why we do this and kind of the theory behind it. Alright, so what we have is, well, the problem is an area problem. Right? The preceding problem touches on the second fundamental problem of calculus. Alright, and we're going to get to that in the next video. We're going to talk about, well, how can I find this area if it's not a nice, pretty geometric shape? Well, what we do is we have to break it down into shapes we can do. Right? And we'll do that in the next section, next video.